So here in Python we have our ideal impulse response, and we have the 0.33 times pi that we calculated before from here. Here we have our Kaiser window, length equals 32 and beta equals to 8. We are multiplying the ideal filter and the Kaiser window, and here is the impulse response of our filter. So the frequency response of this filter is given here, and we see that our stop end, which starts at 0.5, has indeed still enough attenuation at about minus 80 dB, and if we take the 3 dB as the limit for our passband, it goes up to the normalized frequency of 0.3. Going back to our downsampling example, where we downsample from 44.1 kHz to 22.05 kHz sampling rate, the normalized frequency 0.5 corresponds to 11 kHz, and the upper limit of our passband is 0.3 or 6.6 kHz. This now looks like a usable filter for our application. This also shows why the usable frequencies in a time discrete representation is always clearly lower than the Nyquist frequency. So we need filters which have transition bands.